If you're a fan of industrial equipment, and let's face it, who isn't, you're going to like this next one. We're going to go inside the beta lab of Applied Materials with Charlie Gay, who runs our solar division, and see how they make these large solar panels that measure 61 square feet.
In the marketplace, the market is about energy. So we're not selling from one scientist to another. We're selling a solution for making electricity that competes with gas turbines, combined cycle designs, or peaking turbines. It's as simple as the same mantra of Intel inside. The scientists who worried about the material. As the energy business goes, competent companies like Applied Materials are involved in understanding the science behind the material. I want to know if this power plant's going to last for the next 25 to 50 years.
Output and performance is their main concern.
So it's not about which semiconductor layer, it's about the cost, and it's about the durability of this package. The conveyors move the glass, keep track of where the glass, each sheet of glass, where it's been, where it's going, what the next station is going to be, all the way through the final test. You can actually see the glass moving now. And the conveyor sets need to lift the glass up into this, what's called triple stack load lock. And this is positioning the glass then that goes into a chamber.
That's the oven, right? Isn't it?
And that heats the glass up prior to the glass and pulls the air out of the chamber. So from that point forward, the glass is hot and under vacuum. Goes into a center cylinder where there's a robot sitting inside of the vacuum. And that robot then will move the glass into a coating chamber. The boxes that surround the cylinder, a typical Sunfab factory has 7 of these coating chambers clustered around that central cylinder. It's also a way that if there's any servicing going on one of the chambers, all the other chambers are operational. If they were all lined up in series and one chamber in the middle of the sequence needed to be cleaned, then it stops all the other ones. This is the size of the sheet of glass that gets processed in the CVD equipment and through all of the rest of the Sunfab line.
That's one big piece of glass.
It's 61 square feet in size, and there's a huge cost savings that happens by processing the glass on this large area. It essentially takes advantage of the fact that the uniformity of coatings can be scaled from what's been developed in the integrated circuit industry for individual wafers of silicon to this entire surface. And that's where the power of the technology and scaling has been that in some of the thin dope layers on these modules, the layer maybe is about 100 angstroms of thickness, which means 30 atoms. 30 atoms uniformly deposited from one side to the other across this entire surface. So it's an incredible opportunity to scale technology with very thin layers being so controllable over such large surfaces.
Now one thing, this is a question everyone wants to ask Applied Materials. You talk to like 25% of the analysts, maybe a few more, and they'll say, amorphous silicon? Who cares, right? They'll say the thin film will be dominated by CadTel, people like First Solar, or SIGs, and crystal will be big. Just the efficiencies are higher. I imagine you have a different opinion on that.
Sure. Essentially, all of these technologies are coming down in cost. What's important is what is the technology set that can scale? And it can scale both to make the module, so that you get the advantage of the large area of the module size, and can scale with the advantage of large area in installing the module in the field. There's nothing today that's commercially available that reaches this scale. And what the industry is about is getting to scale, both to follow the learning curve for the cost reduction, and not only to make, basically half of the cost of an installed solar array is in this module. and the other half is in all of the work that is done in the field for the structure, the labor, the wiring, the cement, the
assembly
steel.
and construction.
If you're out in the field and it's raining, you just want to plug these things together as fast as possible. If you've got big ones, it goes a whole lot faster than if you have a lot of little ones. So what people look for is that the cost of making the module is about $1 a watt, and the cost to install the module is about $1 a watt. And the total package, the price of that package at the end of the day is around $3 a watt installed. At $3 a watt, we've got basically 10 cent a kilowatt hour electricity in very large parts of the world,
Okay.
bright sun and less bright sun. So these technologies with the thin film are well on their way already. Some of the thin film companies are below $1 a watt for manufacturing here. The cost for crystalline silicon are falling rapidly. They don't actually have to get all the way down to $1 a watt to be competitive with thin films, because the efficiencies tend to be about twice as much as the thin films. Every day that goes by, the cost of fossil energy goes up. Every day that goes by, the cost of solar comes down. So no matter where you are, those costs are approaching each other and transitioning to where solar will be less expensive than the alternatives.